Today we'll be describing light and its properties. Now, late in his life, Albert Einstein wrote, "All the 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta? Of course, today every rascal thinks he knows the answer, but he is deluding himself." He also said, "These days every Tom, Dick, and Harry thinks he knows what a photon is, but he is wrong." And finally, every physicist thinks that he knows what a photon is. I spent my life to find out what a photon is, and I still don't know it. So don't feel too bad that if at the end of this video, light still seems mysterious to you. Now, photons are the carriers of light, and a natural question is, what are photons? But we really can't answer that question. The best we can do is describe what photons and light do, and that's what we're going to be going through here today. Alright, so to describe how light is an electromagnetic wave, we need to discuss, well, what do we mean by an electric field, a magnetic field, and then how we can get, an electromagnetic field or light to actually come out of this. Alright, so if I have here, just say one little electron. So I just have a stationary electron. This electron is going to have an electric field coming out like this. So here I just have an electric field, and this is for stationary electron. So if this electron is not moving, it has a stationary electric field. So it has electric field and it has no magnetic field. Now, let's say I have here my electron, but now this electron is moving. So this has some velocity which is not equal to 0. Okay, so the electron is moving along. And in this case, what we're going to get here is actually a magnetic field. And it's actually, if you've had any physics, you may have heard of the right-hand rule. So if the current's going this way, it curls around like this. So we'd have this magnetic field kind of curling around like this. Okay, so there's this magnetic field which actually develops. And in this case, I will have a magnetic field. And this is for a moving electron. And in this case, this is going to be a current. So you may have built one of those little electromagnets in school. You take a piece of wire, hook it up to a battery, wrap it around a nail, and you can make a magnet by passing a current through a wire. And that's what actually happens here. We have the electron moving along here, and this is creating a magnetic field. Now, it's important to realize that there is, between these two, there's not much of a difference. So you might be saying, well, the electron's moving, but it's moving because of relativity. All right, now to just explain how simply setting the electron in motion creates a magnetic field, we really need to just delve just a little bit into special relativity here. So here I have my electron, and here I have my observer. All right, so if both of these are not moving relative to each other, this person down here sees an electric field for the electron. Now, if both of these are moving along at the same rate, they're at rest relative to one another, and the little person still sees the electron just having an electric field but not a magnetic field. So because the difference between the velocity is 0, from special relativity, there is no relative motion between the two. Therefore, this person sees the electron at rest, the electron sees the person at rest. Now, on the other hand, let's say you are sitting still and the electron is moving past you. Well, now that there's this relative motion between you and the electron, you now see a magnetic field here. Okay, so long as this is moving. Now, on the other hand, let's say the electron's sitting here minding its own business, but now you are running past the electron like so. Okay, so the electron's in relative motion to you, so you actually see a magnetic field. Even though you might say, well, hey, I'm moving, but the electron's at rest. In this case, you actually do have a magnetic field here because you have motion relative to the two of you. And this is just a consequence of Einstein's relativity. And actually, if you go through all the very messy calculus, you can actually show that you basically do a what they call a Lorentz transform of the electric field, and as you're moving past it, it becomes a magnetic field. So this is why electricity and magnetism are not two separate forces. They're really two sides of the same coin. If you're stationary relative to your source, you get an electric field. But if you are moving relative to the source, or the source is moving relative to you, you now see a magnetic field there. The last thing is what we would get for an electromagnetic field. And actually, I should say electromagnetic wave. So in this case, what we're going to have here is, let's say I have my electron, and we're going to keep my little observer here stationary just for simplicity. And let's say instead of moving this electron at a constant velocity like this, he is now accelerating. So he's going back and forth and back and forth and back and forth like this. And because of this acceleration, you see varying amounts of electric field, varying amounts of magnetic field, and it's actually one of the consequences of all the equations that if you have a changing magnetic field, you create electric field, and if you have a changing electric field, you create a magnetic field. So because of this, this is what actually creates the electromagnetic wave. So you have this acceleration back and forth of this. So essentially we have the electron here going up and down and up and down and up and down, and from this is where we get this electromagnetic wave, and of course this right here, this would be light. Okay, so light, and when I'm saying light here, this does not just mean visible light that you're seeing right now, but it also includes everything from the infrared, visible, ultraviolet, X-rays, gamma rays, radio waves, microwaves, all those. It includes all of those fields there. So in this case, here we have the electron accelerating. All right, and accelerating just means that the velocity, the speed of the object is actually changing here. So now how we can actually produce this, now if you are using an antenna, for instance, for your cell phone, how it produces electromagnetic waves is, in an antenna, we have, a hunk of metal here, right? So there's basically a hunk of metal. And what you do is you apply varying current, varying voltage, right? So basically your voltage is going to be proportional to the sine of omega t. So, right, that's essentially what we're doing, is we're just putting some sine wave. There's going to be some, more complicated than that for real life, but basically we're going to have some time varying voltage here. This is going to apply a different electric field inside of there, and then the electrons are going to go back and forth and back and forth, and they're going to be oscillating back and forth inside of this, and they're going to be oscillating at that frequency that you want it to emit at, and that's going to be emitting the radio waves, and those radio waves go out, they go to your cell phone tower, you pick them up, and then from the cell phone tower it comes back to your cell phone and you pick it up. And then what happens on the other side here, so here is my electric field going this way, and then on the other hand, there's my other antenna here, and then these fields get picked up by this, and then it goes out, and then you measure a slight little varying voltage or varying current on the other side. It goes through a whole bunch of circuitry, everything gets amplified, and then you can hear your conversation on the other end. So that's how antennas work. You have a time varying electric and magnetic field that are produced because the electron is being accelerated inside this antenna. It gets emitted from the antenna, and then it gets picked up by another antenna and then spat out. All right. So the way the wave nature of light was eventually proven was that there was something called the Young double slit experiment. So what we do is we have here, essentially a long continuous thing, but there's two little pinholes in there, two little slits. And what you do is you apply light on this one side. So you have the light coming in essentially like this, and really you can do something like this in water quite easily. So you have essentially a water wave coming in here, and then it hits these two little slits, and then the wave starts spreading out. So we can draw, just like this. Here's the wave coming out like so, and it just keeps on expanding like this. Okay. So that's my one wave, and I'm just going to draw this second wave here in a different color just so it's a little bit easier to see. And then on this side, this wave starts coming out. So what we have there is these two waves, and by the way, what I mean by all these little lines, it's essentially the peak of every wave. Essentially what's going on here is here's my wave coming out, and every time I draw one of these little lines, this is the point I'm referring to. And where you see basically the midpoint between the lines, that would be this little trough over here. So the midpoint between the lines is the trough, the peak point is where the peak is of this wave. So what happens on the other side, then we have a detector here. So here's my detector, basically a screen that you can see what's going on here. And if we look here, and of course this is just hand drawn, so it's not going to be the best, but there's certain locations where these lines kind of line up like this, right? They kind of line up like this. Here's another one that goes like this. Here's another one that kind of goes like that. So there's these points here where you see that all the little lines cross, right? So all these little lines cross here, and these are going to give you constructive interference. So where the constructive interference, essentially you have this wave plus, another one. So you have this second wave going up and down like this. And these are what are going to be termed in phase. And when you get that, you're going to get, a much larger wave. So you're going to see bright spots at these locations. On the other hand, in between there, you get the peak here essentially lining up with the trough. So essentially what we'd have here are these two kind of locations in between where the peaks and the troughs kind of match up. And that occurs in the mid portion there. Okay, so for the green, this is going to be the destructive interference. So in that case, I would have something along these lines. So here would be my original peak like that. But then in this case, now it would be looking kind of like this. So I'm adding these up now, and now I have my peak and my trough matching up. And what happens in this case, when I add these two up, I essentially get nothing. So the two waves just cancel each other out. They're 180 degrees in phase, and we see this. So when we look at this detector over here, what we wind up seeing, so this is going to be my detected pattern, is over here we have like a little peak, a trough, slightly bigger peak, a trough, bigger peak, and down like that. So this is where we have my constructive interference over here, and then these points down here is when I have my destructive interference. And this is something that waves do. We can very easily show this in water, but we can also see this in light as well, and that was a big view why light was actually had a wave nature to it. So since light was a wave, they figured like water waves or sound waves, all of these have to travel in a medium. And what they figured for light was, well, if light is a wave, it has to travel through a medium, and this was called the luminiferous ether. And the scientists at the time, Michelson and Morley, back in the 1800s, decided to try and measure what properties of this luminiferous ether and basically see how much dragging is going on. If you think about it, if you are moving along in the wave, the sound is going to be carried, with the wind or against the wind. It's going to travel at slightly different velocities because, the wind is going at different speeds relative to you. So if you're going, talking into a windstorm, the sound is not going to travel as fast out in front of you as it's traveling behind you. So that's what they were trying to measure. And the way they did this was called the Michelson-Morley experiment. So what they did was they had here a light source. So here's my little light source. Okay, so that's my little light bulb. And they'd have here this little, what they call a half-silvered mirror. So the light would only go about 50% of the time. So this is what we technically call a beam splitter. So basically we have here a 50-50 beam splitter. So the light has 50-50 odds of either just going straight through or being reflected off like this. And then over here we have one reflector, and over here we have another reflector. And then this would be your detector over here. So what happens here is the light goes through, so here's my light. So my light is coming up like this, and then it hits the 50-50 beam splitter. So half of it is going to bounce this way, and half of it is going to continue up this way. Okay, so this right here is my very, very thick beam, right? So that's the very thick beam, and then down here the intensity has been reduced by half. So then it hits these two mirrors. So right here, these are just regular mirrors. So it hits those mirrors, and now they bounce back. I'm just going to use a different color here just to show this. So these bounce back off the mirrors here. So it bounces back from this mirror, and I just moved it over slightly just so you can see the difference between the two. They would really just be overlapped if everything was aligned properly. So these bounce back off the two mirrors, and then they hit the 50-50 beam splitter again. And again, you have those 50% odds of the light either bouncing off and going this way or continuing on. Now we're only interested in the light that actually, this one continues on and this one bounces back off. So essentially what we get here is now a stronger beam which hits the detector here. So some of this bounces off and then goes through this one over here. Some of that bounces this way and some of it goes through, but we basically get about 25 of, well, 50% of this, 50% of this. So you're going to get about 50% of the intensity actually hits the detector over there when all this is said and done. So anyway, we have this detector here, and now the reason these are angled at 90 degrees relative to one another is so this way you can see how much the speed of light actually changes because of the relative motion of the Earth around the sun. So remember, of course, here is the sun, and the Earth is going around the sun, right? So the Earth is going around the sun. So that was known back in the 1800s, of course. So the Earth here is going and here you can say this is January, this is June. So the Earth is going here about 30 kilometers per second. And then down here, 6 months later, it's now going to be heading the opposite direction, so negative 30 kilometers per second. This is the speed of the Earth. So essentially what happens is, here's my little detector thing. And if I were to view how much these waves move because of the moving through the ether, you would expect a difference, if you do your measurements here in June versus January. Okay, so that 6 months difference you can actually start measuring. Additionally, this stuff here was actually floated on a large pool of liquid mercury. So what you could do is you would have your whole table floating there, and then you could just take this and rotate it around by 90 degrees and see if the stuff actually moves around within the experiment itself. Of course, the Earth is also spinning, so it's not just the Earth going around the sun that you hope to measure, but of course, the Earth itself is also spinning. So there's the Earth, and that's also spinning, but its spin is much slower. It's only about 0.5 kilometers per second. So it's about an order of magnitude smaller for the Earth spinning, but over the course of a day you should hopefully be able to measure that. And they were looking for this, effect. So remember that light is a wave, right? So the wave would come in, and if you go up here and if the ether is coming with you, then it would take maybe a little bit longer for this journey over here, because some of it would be sped up and slowed down. Over here you would expect no effect, because you would kind of be going perpendicular to there. And you would basically just turn this thing around here and then hope to see some kind of a change in your detector, right? Because as you move this around, or as the Earth's speed relative to the ether changes, then you would see some effect here on the detector, because the light would be moving at slightly different velocities for this arm versus this arm. And that's what they were looking for. Is there a change in velocity depending on which direction you're actually heading? And they did very careful experiments, and they found absolutely nothing. So this is one of the rare times in science where actually getting no results was a good thing, because they set out to look for properties of this ether and they found absolutely nothing, and eventually they won a Nobel Prize for finding nothing. Really helped Einstein figure out his whole theory of relativity, that the speed of light is constant no matter how fast you're actually going, right? So if I'm going around the Earth here, this is 30 kilometers per second versus over here, so that's a 60 kilometer per second difference. And this difference here really amounts, so basically 60 kilometers per second, so the change in velocity there, that's the same thing as saying 0.02% the speed of light. All right, so a 0.02% difference, that should be something that's easily measurable, even back in the 1800s, but they saw absolutely no effect here. And this, helped Einstein figure out that, well, it doesn't matter how fast you're actually traveling, but there is no change in the velocity of light relative to your motion here. So actually, just going back to my little person here, so if I'm sitting here measuring the speed of light, I'm going to measure the 3 times 10 to the 8th meters per second. If I'm traveling along at 99% of the speed of light here, or you're going really fast, then he would be measuring exactly the same speed of light, no matter how fast a little guy is actually going along there. Now, as for light, we were saying it's a wave. So the properties of this wave. So here's my wave, like so. So there's 3 properties of this wave that we can measure here. So first of all is the wavelength. Okay. So there's the wavelength here, which is represented by the Greek letter lambda. Okay. This is wavelength, and it has units of length, unsurprisingly. So in other words, you're going to usually see this in terms of meters, or micrometers, or nanometers. Those are going to be your general units that you're usually going to see for wavelengths here. The next thing is the frequency. Basically, this is the frequency. It's basically how often it repeats. Frequency is measured, and this is the Greek letter nu. So this is my frequency. All right, and this has units of 1 over time. All right, and the usual units on this are, of course, going to be hertz, and this is usually just Hz for that. And and I should say here, a hertz is equal to 1 over a second. So that's, usually you hear of hertz and cycles per second. That's what they're actually referring to there. Now, frequency refers to how often something repeats. So if we're just dealing with like a 1 hertz signal, then you're going to have something that goes 1 1000, 2 1000, 3 1000, 4 1000. So it's going to go like that. Okay, so that's going to be a 1 hertz signal. But if you're dealing with something that's 10 hertz, you're going to have 10 cycles per second. So you're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something along these lines. So you're going to have something which repeats much faster. So for instance, here this would have this certain frequency. But if I were to draw something like this, now my frequency is much higher. So this one here, this is high frequency, and this one here is going to be low frequency. Now, between the two of them, so as you can see right here, the reason this is high frequency is because it repeats much more often. This is lower frequency because it takes a long time to actually go between their all cycles. Now, what you notice right here is that as my frequency increased, my wavelength actually decreased. So this is actually a very important relation between the frequency and the wavelength, is that the frequency here is inversely proportional to the wavelength. So here I have low frequency and a long wavelength, and here I have a high frequency and a relatively short wavelength. Okay, so they're inversely related to one another. And the relation between them, what is my proportionality constant here, is actually the speed of light. So in this case, the equation is that the frequency is equal to c over the wavelength. And c, of course, is the speed of light. And actually, for more general things, if you're talking about speed in the air, this would be the speed of whatever wave you're talking about. So, for the speed of light is 3 times 10 to the 8th meters per second. You're talking about the speed of sound. In that case, you'd be doing 300 and some meters per second. So whatever the speed of your wave actually is. But generally, this is usually just written as that c is equal to lambda here times nu. And I really should say here that even though this looks like a V, this is the Greek letter nu right there. So that's the Greek letter nu. All right, now the third thing that we can actually measure here is the amplitude of the wave. Now there's a couple ways of actually talking about the amplitude. You can either do here the peak-to-peak amplitude, talking from here, the peak to the trough like this. So that's like what they call the peak-to-peak amplitude. You can also talk about just the amplitude from the midpoint here, which would be like your 0 to the peak. That could also be an amplitude. And then if you're also dealing, especially if you're dealing with the energy intensity in the wave, then you might be talking about just the root mean square amplitude. For our purposes, just to keep things simple, we're going to be talking here basically just the peak to peak. Okay, so just for this amount right here, we'll just call this the amplitude. So what you can see right here is that here we have the amplitude of this wave is larger for this one is shorter for this one. But here the amplitude has no relation on the energy of the wave. All that means is that the amplitude is how bright something is. Okay, so amplitude. Okay, the intensity, so how bright. So obviously if we have something that's very bright, here I'm making things dimmer, we have less amplitude. Now the intensity here, this is not determined by how much energy is actually in the wave. All that's telling is like how many waves there actually are. So that would be the amplitude right there. We're generally not going to be worrying about that. All right, now the next thing that we can actually figure out, and this is very important, especially when we're doing with energy in terms of transitions and everything, is what is the energy of this photon? And it turns out, and we're not going to show how we prove this, but just give the equation here, is that the energy of this wave is going to be proportional to the frequency, and we can just write this as E equals h times nu. Okay, so E is the energy of my light photons. H is my proportionality constant, and nu is my frequency. So H is what we call Planck's constant, and this is equal to, so H is Planck's constant, and this is equal to 6.626 times 10 to the minus 34 joule seconds. Okay, so joule is a unit of energy, seconds of course is unit of time, and notice that this is joules times seconds, not joules per second. So that's important for this. And again here, my frequency, that's 1 over seconds. So that's joules times seconds divided by seconds. We get the energy here in joules. Right. So anyway, this is just a proportionality constant, and it's actually a consequence of quantum mechanics over here. All right, now what I can actually do is, so I've related the energy is equal to h times nu. Here we also have this relation here between the frequency and the wavelength. So we can actually combine this equation, so h times nu, and we see that nu is equal to c over lambda. So I can just as easily rewrite this as E is equal to hc over lambda. And these two equations are exactly identical. Okay, so if you know the frequency, you can use this one. If you know the wavelength, you can use that one, or you can always just convert between the two and make it work. Either way will work perfectly fine. Now, one little thing, which is actually kind of cool here, is what happens when light enters a medium. And what do I mean by medium? I mean glass or water, or something where it changes from going through air or vacuum. So in this case here, we're going to have here, okay, so let's say this here is a vacuum, and then here I have a piece of glass. In this vacuum, we have that the speed of light, is moving at its constants, consequence of special relativity. In the piece of glass, on the other hand, light slows down. I'll call this C vacuum is equal to C. And in this case, C for the glass is actually going to be less than C. So what happens here is my light coming in like this, and it hits the interface. When it hits the interface, the light actually starts slowing down. So when it starts slowing down, it's just like if you're driving in traffic and the cars are nice and evenly spaced, then you hit a gaper's delay, and then all the cars start backing up because they simply can't go as fast. So what's going to happen here is that now the light is going to be squeezed closer together here. And then let's say I have here vacuum on the other hand. So I have vacuum on this side again. And now this is going to keep on until I hit the interface again. And now you're at the end of the gaper's delay, it's pure sailing. So what happens, you now start spreading out. You have longer wavelengths here. So what happens is that the speed of light actually slows down. And this is what we call the index of refraction. So when light always slows down. It can get slower, but it will never actually speed up if you happen to be going in a medium. So how does this actually relate to my energy of my photon, my frequency of my photon, and my wavelength of my photon? How are these different inside the glass versus in the vacuum here? Okay. So first of all, the energy is going to be, so this is energy in the vacuum, is going to be equal to the energy in the glass, okay? Because remember, energy is conserved, so I'm not losing any energy through this transition. Energy is conserved, so the energy inside the vacuum is going to be equal to the energy inside the glass. Here's the energy related to my frequency. Notice right here, this is a proportionality constant. This is Planck's constant. It doesn't change depending on your medium, so this is always the same. So my frequency is going to be the same in this case. So the frequency in the vacuum is going to be equal to the frequency in the glass. Okay? So the frequencies are going to be the same on both sides. But now the wavelength, this is going to change, because we said right here the speed of light actually slows down when you enter a different medium. All right, so the speed of light is going to slow down here, and since this isn't changing, that means that my wavelength has to change the same way. So here the energy has to be the same. This is the same, speed of light slows down, therefore my wavelength has to shrink. So therefore, this wavelength over here is going to be greater than, so the wavelength in the vacuum is going to be greater than the wavelength in the glass. So when you go into the glass, as we could see here, just like because we said like that little gaper's delay, the frequency, or I should say the wavelength here shrinks down. Now this is actually very important for something termed optical lithography. So when you're making computer chips, the way they do this is by taking a slab of silicon. Okay, so let's say here I have a little slab of silicon. So this is my silicon. And then you have up here actually a UV source, so ultraviolet radiation. And then in between there you have a mask, which is essentially like a negative. So it produces a little shadow. So essentially like putting my hand in there, there's a little shadow that's actually being produced because of this mass. So you have this kind of a little funky mass there with all your little circuits and stuff on there. So your light is traveling through this and producing, a shadow, which, produces its little, circuit diagram on there, making your transistors and whatever. One of the big pushes in computers is to make smaller and smaller transistors. Now, the only way they can actually do that is by using shorter wavelengths of light. All right, now the general thing is when you're using these shorter wavelengths of light, if you want to try to extend the lifetime of your materials and everything, you don't want to have to put in a whole new optical system, because you can't just tune down the wavelength on the laser. You need to put a whole new optical system in. So instead what they do is, for this, they put a little blob of water right above here. Okay? So you put this little blob of water on there, and so this is your H2O. And the reason they use water is because it's cheap and you can make it very high purity. So you put a little blob of water on top of there, and now when the light is coming in, of course it's from the air, of course, but then it hits this little blob of water, and then the wavelength shrinks, and now you can get smaller component sizes onto your little computer chips. And this is one way that they're able to extend the life of all these optical machinery when they're trying to make very small components in terms of silicon. So this is how you can actually use that.